started. What we're going to be looking at today is sequences. So that's my goal. Going to look at evaluating them, which we kind of talked about yesterday, but not very much. We're going to look at what are called the limits of a sequence, which means I'm going to be bringing back some knowledge that you should have picked up in your past math career. And that is how you find limits of things. And sometimes when you haven't used them for a while, you kind of get rusty and forget a little bit. So let me kind of make up my own question. Let's suppose that we have a sequence and it's described by this formula. And you might be asked, for instance, to find the first 5 terms. So let's assume that that was the first question, question A, find the first 5 terms. And let's say that they want the answers to be left as fractions. And I could certainly do these guys, by hand. I could plug in 1. So 1 squared plus 1 is 2. 2 over 2 gets me 1. Plug in 2, that's 5. 2 squared is 4. 4 is 5/8 then. If you plug in 3, you get 10 on the top and 18 on the bottom. And 10 over 18 gets you 5/9. If you plug in 4, you get 16 plus 1 is 17 on the top and 32 on the bottom. And then if you plug in 5, you get 26 on the top and 50 on the bottom, which is 13 25s. So, or you could do, because I'm not very good at counting, you could make sure that your calculator is set up on sequences. And then you could go second list, go to operations, choose option 5, which is sequences. And then to do something like this, you have to be careful with brackets. So bracket n squared plus 1, close the brackets, divided by, start another bracket, 2n squared. Then you go comma, n, comma 1, comma 5, and with a bit of luck, and I didn't get my bracket screwed up, we get them. And they are not fractions, but if you hit math button, option 1, it turns your answers into fractions. 1, 5/8, 5/9. Hit the scroll over, 17/32s. Hit the scroll over, 13/25s. Now, what would you want to do with sequences? Well, let's say you want to find them. We know how to do that. If somebody said to you, yeah, let's find the 100th term. Well, it's a bit messy, but couldn't you do 100 squared plus 1 over 2 lots of 100 squared, right? Now, in that case, I wouldn't use this, right? Wouldn't that take forever in the day and it would be messy? I would just do it the old-fashioned way. So on the top brackets, let's actually do it in 2 stages. 100 squared plus 1, which gives me that number on the top, and it gets me that number on the bottom. So if you're given the formula for a sequence, you can find the first 5 or 25 terms. You can find one very large term, like the 100th term in the sequence. But you're also very often going to be asked to find the limit of a sequence. And what that essentially is what's the limit as n tends to infinity of this guy? That's the general one. In this particular question, then, we want to find the limit as n tends to infinity of this fella. And this is where stuff you've done in the past comes in. It's been a while since you did limits. In fact, I believe for most of you, you did a little in Calc 2, I'll take that back. But for most of you, wasn't Calc 1 where limits get introduced? right? And the reason you might have seen calc too is, can you remember those intervals from 1 to infinity? Can I, if you don't mind, I'm going to just do something here with the participants, and I'll mute you. Okay. So if you want to answer a question, just hit spacebar. Okay. So where was I? So we did it in Calc 1. That's where we mostly did it. And there was a little bit in Calc 2 where you had to do indefinite integrals like 1 to infinity, right? So you did a little bit there, but not so much. So we have to figure out how to find this fella. And there are a couple of techniques that are going to be quite useful, right? In fact, there are going to be 3 techniques. So I'm coming back to that question. But let's just remind you what the 3 major techniques are going to be. The first one, excuse me, I call brute force. In brute force, you essentially just make n infinity and do a calculation. And I'll show you what that looks like in a minute. The second technique is very helpful when you're dealing with fractions, and that will be divide the top and the bottom. I guess I should call them the numerator and the denominator by a power of n. And then you do brute force. So that technique would be, and I'll show you one, you divide the top by n cubed and the bottom by n cubed, and then you make n infinite and see what you get. And the last one is L'Hopital. Now, there are other techniques. One of them is factor and cancel, but factor and cancel is probably not going to be used much. So I don't want to clutter up your mind with a technique you're not going to really use. So let's show you a brute force question. Suppose I wanted to find the limit as n tends to infinity of 3 over n squared plus 1. Well, according to brute force, you would just essentially find that. Now, when you deal with infinity, you have to be really, really careful about what you can do and what you can't do. Would you agree that infinity squared is still infinite? And if you add 1 to it, it's still infinite. And so it's okay to say that. And in these questions, the ones that use brute force, your answers are almost always going to be 0 or infinity, right? 3 on the top divided by infinity. Would you agree this would be 0 would be the limit? Any number over an infinitely large number is going to tend towards 0. Now, on the other hand, if you were given the limit as n tends to infinity of e to the power of n over 5, brute force would be e to the power of infinity over 5. Now, isn't e to the power of infinity still infinite? And infinity divided by 5 gets you infinity. We don't normally say the limit is infinity, we say it diverges. But, you know, in this case, it diverges because the limit is infinite, right? You're familiar with that technique? Right. Sometimes it's just easy to plug in infinity and see what you get. Wish it was the only technique because it's kind of easy to do because your answer's either 0 or it doesn't have a limit, right? It's infinite. Now, divide the top and bottom technique tends to happen when you have fractions. Suppose that was the sequence. Now, if I just plugged in infinity in here, so let's do it as if I was trying it with brute force. It'd be 2 lots of infinity cubed plus 1 over 4 lots of infinity to the 4 plus infinity. Right, infinity cubed doubled and add 1 is still infinite. Infinity to the 4 times 4 plus some more infinities is still infinity. And no, it's not 1. Agreed? Infinity over infinity is just not on because some infinities are bigger than other infinities. I know it's a weird idea, but they are. So that's why brute force would not work on this case, but it did work in these two cases. Are we comfortable about when you can use brute force and when you can't? You can use brute force when you've typically got a number, an infinity, or an infinity and a number, right? You can't use it when both things are infinite. You just don't want to go there. So I'll return back to that question. And the technique I'm going to use is to divide the top and the bottom by the same power of n. Okay? By the same power of n. So you look at the highest power on the top, which is n cubed, and you look at the highest power on the bottom, which is n to the 4, and one of those you should choose. Which one do you want me to choose? N cubed or n4?
Is it n cubed?
Yes. Is it n cubed? Yeah. Pick the smaller one. If you're not happy, there's the rule. Pick the small one. Actually, it'll work if you pick the big one, but pick the small one. Make your life easy, right? So if one of them's n to the 5 and one of them's n to the 7, pick the n to the 5. There's a rule. Stick to it. Keep life simple. Now, let's see what this becomes. Well, it becomes a limit as n tends to infinity. If you divide this by n cubed, you get 2. If you divide this guy by n cubed, you get that ugly looking guy. You divide this guy by n cubed, you get 4n. When you divide this guy by n cubed, you get that. And then you do brute force. And brute force is my term for you make everybody that's an n infinite. So let's see what we get. 2 plus 1 over infinity cubed. 4 lots of infinity plus 1 over infinity squared. Okay, 1 over infinity cubed. Isn't that 1 over infinity, and isn't 1 over infinity 0? Or at least its limit is. Isn't 4 infinity still infinite? And if you add 1 over infinity squared, you're just adding 0 to it. So you're not going to make much. So that means we have 2 over infinity. What does 2 over infinity get you? Correct, a big fat 0. And so we know the limit. In this case, 0. Let's try another one. Suppose we're still using method 2. Let's suppose we want to find the limit as n tends to infinity of 2n cubed plus n over 14a cubed plus n squared. And we're going to divide the top and bottom by a power of n. Now here the choice is much more limited. The biggest power on the top was n cubed, and the biggest power on the bottom is n cubed. So we don't really have a choice. Don't we divide top and bottom by n cubed? So that gives us the limit as n tends to infinity of 2 plus 1 over n squared plus, on the bottom, 14 plus 1 over n. And then when we do brute force, we have 1 over infinity squared there and 14 plus 1 over infinity there. But isn't 1 over infinity squared 0, and isn't 1 over infinity 0? So essentially, we have that. And I'm writing down more lines than you would ever want to write down. But can you see that the answer is 1/7? So if you get sequences made up of powers and they're fractions, I would probably say do method 2. Right? If you get a 5 over n squared plus 1, do the brute force method, right? If you get an n cubed plus 1 over an n squared minus 2n, you know, that kind of thing, use method 2. So there are 3 methods, right? The third and final one is called L'Hopital. So we need to kind of show you when that would be used. Use L'Hopital when at least one or more of the terms is not a power of n. So if you have an e to the n, or a sine of 1 over n, or 2 to the n, right, something like that, then you would think about it in that case. So how about this fella here? Okay, there's an e to the n. Anytime you see a power of e, a sine, that kind of thing, you're probably going to go L'Hopital. And technically, you put a little L. That just means for people who are looking, oh, you're using L'Hopital rule. So put a little L above your equals just to indicate that. Now, according to L'Hopital, don't you basically just differentiate the top, which is pretty boring, and you differentiate the bottom, and then you try brute force. Well, if you try brute force, can you trust me? It's infinity over infinity, which is called indeterminate form, so you don't do it yet. So what do? Well, you keep going. And you try brute force again, but it's still infinity over infinity. So you do it again. Only this time, when you do brute force, you find out the limit is infinite. Do you want to see another one of those, or are you comfortable with L'Hopital? What do you want to do? Your choice.
Can we do another example of that?
Yeah, let me look at the homework. Maybe I could pick one, you know, a little bit more interesting than the ones I've just picked. They probably won't have one, unfortunately. Boring. Oh, that's a really good one. Double check that one. Just boring. Interesting. No. Ooh. Yeah, I was going to pick a different one, but I saw that one and it kind of changed my mind because I was going, ooh, that's an interesting looking sequence. Would you agree the log of infinity is infinity? So brute force doesn't work. 3n is just infinities as well. The reason I like this one is that it has ugly fractions in it. So if you differentiate the natural log, don't you get 1 over the thing? Be careful here. We're going to differentiate the natural log of 3n. And it is 1 over the thing, but isn't it also times something? Because it's a general. You know, like if you differentiate the sine of 3x, you get the cosine of 3x, but don't you get an extra times 3? So don't you get an extra times 3 here? And I'm taking this really slowly. Again, you probably won't need all these lines. 1 over the 10 and 1 over n. You see the 3's cancelling? Oh, wait a minute. Isn't 1 over n over 1 over n? 1. And so I don't even need to do the infinity bit, which I wasn't expecting until it happened. Right. Let's do one more of those. The one I was going to do before this one. That one. This one has to be L'Hopital because it's got an e to the minus 3n in it, right? But to be a L'Hopital, don't you need to be a fraction? So we're going to have to do some algebra on it before I even try and Start L'Hopital on it. What will the e to the negative 3n become when I stick it down here? It's an algebra rule. What happens to a negative power?
It'll just be e to the 3n on the bottom.
Agreed. Remember, negative powers are 1 over the positive. Right? X to the negative 2 is the same thing as 1 over x squared. Be an example of that. Now, I can do L'Hopital on this guy. If I do it the first time, I don't get much. And almost forgot, when you differentiate e to the 3n, you get an extra times 3. Brute force doesn't work on that because you still get infinity over infinity, so I do it one more time. If you differentiate this, you get 3e to the 3n times another 3, so it now is 9. Do the brute force thing, the limit is 0. Okay, so we a little bit more familiar with brute force, just plug in infinity and hopefully you get a nice easy question. Divide top and bottom by powers of n cubed, n squared, or L'Hopital. At the end of the day, don't they all finish with a brute force by you plug in infinity and see what you get? Okay.
Sorry.
Any question? Yes. Christian.
How did you get 2/3 in that again, or did you just put in 2 numbers?
Oh, I differentiated e to the 3n. When you differentiate e to the 3n, you get e to the 3n times the derivative of 3n, which is the extra 3. So that's where that came from. We call that, it's in differentiation, it's called the chain rule. If somebody said differentiate the sine of 2x, you would get the cosine of 2x times a 2 because of the 2x bit. So that's what was going on there. Any other questions? Let's jump over and look at homework questions. They're the best way to see what the heck's going on anyway. It's a little bit too far ahead. Let's zoom up to the top. That's some definitions, you can do that. Right, can you see this one here is pretty much what you see is what you get, right? You're just going to plug it in at your calculator, do it in your head, and you get a whole set of numbers. And that's typically the way I tend to write my questions. Are we comfortable about this notation, which is basically that's your AN, but you're starting at 2 and you're going to, well, theoretically infinity, but you're only writing down the first few terms. Are we comfortable with how that happens? Right. I've
So
just
that's,
realized
that was from 2 to infinity.
yes, that one was starting at 2 to infinity. There's no reason in the world why it needs to start in 2. They just decided they wanted to. Most sequences don't they start at 1 because that's kind of natural. You know, first term A1, second term A2. But I guess you've got the flexibility. Haven't done anything with negative powers, like negative 1. See that guy there? So let's do this one. A1 is what you get when you replace this n and this n with 1. So we're going to have to do, I'll try this in my head, negative 1 to the power of 0 divided by 1 squared. Okay, let's make your brain hurt. What number is negative 1, in brackets, to the power of 0?
1.
Yeah. So this one is going to be 1 on the top over 1 squared, which is 1 on the bottom. So that would be 1. Let's try the next one. A2. Now, when A is 2, doesn't this become 2 take away 1, which is 1? So negative 1 to the power of 1 is negative 1. Over 2 squared is 4. So that would be negative 1 over 4. Are you happy with that? Negative a quarter? Right. I just realized, right. What do they want this in anyway? They didn't say, okay, so isn't the next number going to be positive again? And it's going to be 1/9. And the next number is going to be negative, and it's negative 1/16. And the next number is going to be positive, and it's going to be 1/25. Now, we call these alternating sequences. Whenever you see a -1 to the power of n, n-1, n+1, that kind of thing, what you're going to get is a sequence which goes positive, negative, positive, negative. Or maybe it starts negative, then it goes positive. And we call them alternating because they alternate between plus and minus values. We cool with that, guy? Right. As long as you put brackets around it. Oh, here's a really cool one. You could just do it in your calculator, but let's try and do it in our head. When a is 1, what's the cosine of pi? Oh, come on, hit the space bar, cosine of pi.
1.
-1.
Well, which one do you want to go for? One of them is correct.
Should be -1.
So -1. What's 2 pi?
That's 1.
What's the next one?
-1.
Can you see that once you've done a few, very often you see a pattern? Now, what's interesting about this particular sequence, apart from the fact that it only has 2 values, is that if I asked you for what the limit as n tends to infinity of that sequence, it's not correct to say that the limit's infinity, because it's not. It diverges. Do you see why we like the word diverges? It kind of covers all possible reasons. You either tend to one number, so you have a limit of 4 or 2.5 or 0 or whatever, or you go off to infinity, in which case you call it diverge, or you do weird stuff like this. Right? You're not going to one number. A very simple example of a divergent sequence would be the sine of n. Right, the sine of 1, the sine of 2, the sine of 1,000,000. Do you know those numbers are pretty random? They just bounce between 1 and -1, and the next number could be anything in that range, and the one after it could be totally different somewhere else. Those count as divergent. Now I need to skip back and show you a guy that you may not be familiar with, although it's hard to tell whether you've seen it before. We're going to look at a thing called factorial. So factorial, something like that. It has an exclamation mark. So if you wanted to get 3 factorial, it's 1 times 2 times 3, and its answer is 6. And if you wanted to get, I don't know, 7 factorial, it'd be 1 times 2 times 3, which I hadn't picked that one now. And obviously that is a pretty horrendous looking number. So you don't want to have to do that by hand, especially if it's a really big factorial. So I'm going to hit the math button and try and find where the heck it is. There it is. It's under probability number 4. Do you see it? So let's suppose I wanted to do 7 factorial. You do 7, you hit math, you go over to probability, and you choose option 4. And there is 7 factorial, and it's a pretty big number, right? It's over 5,000. Are you comfortable with that now? If you have to find 10 factorial or 2 factorial. We go. So let's suppose that I had a sequence, and it was -3 to the n over n+1 factorial, and you were being asked to find, just to make my life easier, you were only being asked to find, to say, the first 3 terms. Now, I could certainly do them in my calculator, but let's show you what the calculation would look like. It would be -3 to the 1 over 1 plus 1, which is what, 2 factorial. And that's -3 on the top, and 1 times 2 is 2, so there's the first answer. Right, if you wanted A2, it would be -3 squared over 3 factorial. That would be +9 over 6, and that would simplify down into 3/2. And A3 would be -3 cubed over 4 factorial. That would be -27 on the top, and 24 on the bottom. I think you can divide them by 3, can't you? So you get negative 9/8. Are you comfortable about dealing with factorials now? I think for a question like that, it might be safer to just do them by hand. You could probably put them into the sequence formula. I'm sure it would work, but I just feel a little bit more comfortable. There's so many brackets involved in typing the thing incorrectly, right? So, I mean, if you were typing that into a calculator, you do -3 factorial divided by 3 factorial. And I don't know if you need it, but I would always play safe and put a 3 in the brackets just to make sure the calculator doesn't do factorial last in the process and, you know, kill over and die. So it's just safer in my brain because I know I make mistakes. Any questions before I move on to a different type of sequence? Are we good?
So if you
Yep.
do problem 6, it doesn't allow you to just add the 1 to the equation. You actually have
Oh,
to,
this one is just my made up version. It's like question 6, but it's not question 6, Christian. So
Okay.
I'm not sure what your question is. Are you okay now?
not really.
Okay, right. Let's see what your question is. I'm going to go back to question 6, and we'll kind of talk through the example that they have. Although these questions change. Anything that's red means that your number might not be 3, it might be 10. So let's suppose I was doing this fella here, right? Now you want to do A1, then what you want to do is replace this n here and this n here by 1. So the top guy would be -2 to the power of 1, which is -2. And the bottom guy would be 1 plus 3, which is 4. And 4 factorial ends up being 24. So that would be kind of the first answer. And then I'd say, wait a minute, that can simplify down. So I would finish with -1/12.
Does simplification impact the answers on WebAssign?
I think WebAssign is fussy. So the answer I would suggest is yes. So 2/4 is going to tell you you're wrong. It wants a half. And so, okay, I don't know if I can actually type this in that way. I want to check it out. Submit answer. Yeah, okay. So it was -1/12. I don't know if you can do this. I haven't tried this yet. That was the unfixed version, right? Going, prove me wrong.
I did get the definitions, but I did find them confusing the way it's written, with the like, as this number gets bigger or something along those lines.
What you're saying, what, for the factorial thing?
Oh no, it was the definitions questions on the top of the screen. I saw you scrolled by them, and I just wanted to tell other people that I found the way that is written to be a little bit confusing. If people should probably read that more carefully than I did.
Okay, so when you come to do question 1, thankfully you've got 5 shots, so you're going to get it right eventually, but it's better to get it right the first time. Yeah. Okay, so let's move on then. And what I want to look at now is a different way of describing a sequence. And the technique, the method that we're going to use is called a recursive relation. And what you do in these situations is that you don't give a formula like this. Right? That's what we've been doing with today, right? If I give you that, can't you find A, 1, 2, 3, 4, 5? You could even find A million if you wanted to and be really awkward, but nonetheless you can do it. In a recursive relation, that's not how the information is given to you. You will typically be given the first term, and sometimes it's called A1. I've seen it called A0. I've also seen it called A2, but they'll give you a number to start with, A1, and let's suppose it's 10. And then they'll give you a relationship that looks something like this. And this is the recursion. What it says is, in English, the next number in the sequence is the previous number add 3. That's how I would read that. So if I wanted to know what A2 is, A2, it would be A1 add 3. It would be 10 add 3. It would be 13. If I wanted to know what A3 is, it would be A2 plus 3, 13 plus 3 equals 16. And one more. If I wanted to know what A4 is, it would be A3, the previous number, add 3, 16 add 3 equals 19. Do you see how this sequence is being generated? Now, you cannot use your calculator, right? There's no easy way to make that happen. At least there's no easy way I know to do that. You just have to do it by hand the way I've done this. Do you also see that in this particular sequence, if you wanted to know A100, wouldn't you have to do the first 99 first before you could get to it? So nobody's going to ask you to find A100 in these, right? Just by the sheer ugliness of the technique, right? It's not really conducive to finding large terms, right? You know, the 100th term in the sequence. But that's what they do. That's one example of a recurrence relationship. Here is another one. And in these ones, you're given the first two numbers, A1 and A2. And they tell you the next number in the sequence is the one just before it, in this case, plus the one just before that. So if I wanted to find A3, for instance, it would be A2 plus A1, which is 1 plus 1, which is 2. If I wanted to find A4, it would be A3 plus A2. Well, A3 is 2, A2 is 1, it would be 3. And one more, if I wanted to find A5, it would be A4 plus A3, that's 3 plus 2. Do you see, you just add the previous two together. Does anybody actually recognize what this sequence is? If I write it down, it was 1 and 1, and then it was 2, 3, and 5.
It's the Fibonacci sequence.
It's the Fibonacci sequence, which is a very interesting sequence that appears in nature and all sorts of weird places. Now, can you realize that for this particular sequence, you don't have a formula in the way that we used to, right? Isn't it a case of a process where there's a relation that is recurring, right? Whatever it is, you do the same thing, but you do it with different terms, right? So you add the last term plus 3, or twice the last term plus 7, or as in this case, that term plus that term. I have just decided to create the Robertson recurrence relationship. And my recurrence relationship is that one. Okay. So I'm going to start with 1 and 1, which are very often called the seeds. And I'm going to use this seed to generate our sequence. So let's find out what A3, A4, and A5 are. A3 is going to be A2 to take away A1, which is 1 take away 1, which is 0. A4 is A3 take away A2, which is 0 take away 1, which is -1. And A5 is A4 take away A3. And A4 is -1, take away A3, which is 0, which is -1. I guess I want to do one more. I'm not quite sure what my sequence is doing here. A5, take away A6, -1. That's 4. -1, take away a -1. Oh, equals 0. Oh, what a boring sequence. I've got a feeling this sequence just bounces between zeros and -1s. Maybe some 1s occasionally. Nowhere near as interesting as Fibonacci, but hey, it's my sequence, so I'm keeping it. You'll have to make your own recurrence relation, right? So Rosie, you're going to have to pick your own one. Call it the Rosie recurrence relation, right? Maybe you'll come up with something more interesting than my boring one. But are we comfortable about how you calculate the values when the relation, the sequence is given in terms of a recurrence relationship? More likely to get a nice single one, but you could get double ones like this as well. We feel good about that? Right. Let's have a look at what that looks like in the homework world then. Okay, keeping track of my time this time. Okay. So question 7 would be an example of that. Do you see it's, you start with a 6. So that one isn't even worth doing. Right, now if you wanted to get the next term, wouldn't it be twice times 6 add 5, which is what, 17? Now if you wanted to get the next term, wouldn't it be twice the previous, twice times 17, and then add 5, which I believe is 39, and then off you go. Although I can't use any of the limit techniques, can't I do it by observation? Would you agree that this sequence is just going to get bigger and bigger and bigger? So if someone said, what's its limit? You would say infinity, right? I'm not using algebra, I'm just using common sense. Yeah. Suppose you get it in the form of a fraction, right? Well, the first one is 3, it's 18. If you want to get the next number, A2, it's the previous number 18 divided by 2, which gets you 9. If you want to get A3, it's the previous number divided by 3, which is 9. Okay. If you want to get A4, it's the previous number divided by 4, which is 3/4. And if you want to get A5, it's the previous number 3/4 divided by 5, which I believe is 3/20. Again, not using algebra, but just using common sense. What would be the limit of that sequence?
0.
Yeah, would you agree it's just getting smaller and smaller and smaller? Right. And so that would probably indicate 0.
Doesn't that sequence shouldn't if we found A2, which is an plus 1, and it's dividing by n, shouldn't that be 18/1 for A2, A sub 2?
Oh, let me check. No, A sub 2. Oh, darn it in space. You're right. I got out of sequence. But yeah, I'm not changing that. You're right. I got out of sequence. I was saying A2 meaning that 2. That means each one of these numbers gets divided by 1 less than I said it was. So that would be 18. So that one there would become 9. Basically, it looks like my sequence just shifts down 1. So that one would become what, 4, that'd be 3, that'd become 3. And then this one here, that would become 4, right? I think that's it. Yeah. Be careful about that. Okay, let's do one of these. First one is 3, which is 8. Now, if I wanted to do A2, it's the previous answer, right? Over 1 plus the previous answer. So what would that be? 8 on the top and 9 on the bottom. Comfortable with that? Previous answer 8 over 1 plus previous answer. And the next one would be some ugly fractions. So I don't want to do that. Okay, for our last. Okay, I just want to talk about this one because I don't have time to do much more. But tomorrow we will do this in a lot more detail. Here is a puzzle that you've probably never needed to do before, because normally you get things and you don't create things. And we are going to create a formula that generates this guy. Now, if you're good at recognizing patterns, these guys so I want to figure out when n is 1, right, you get a fifth. When it's 2, you get a 10th. When you get 3, you get 15th, and 4. And we want to generate that guy.
1
So-
over 5n.
Oh, you nailed it. Right. What I would do in that question would be, if something's the same, it's the same in the formula. So you agree 1 in the top because they're all 1 over something. And then you look for something going in the bottom. Here's one then. Okay.
Isn't it 1 over n squared plus 1?
I like your thinking, and yes, it is. Tell me why or how your brain figured that out.
Normally, I'm not super good with figuring out series, but I have seen something like that before, and I knew to look for it.
Okay, so it's previous knowledge, I guess, right?
So the way we used to do stuff like this, I did a lot of CNC programming. And so you look at the difference in change between each one. Yeah, so you draw that little hoop underneath and then you see what you're adding each time. And that can really help you a lot. And then you look for patterns.
Right, and if you look for that pattern, that would allow you to generate the next answer, even if you didn't know what the formula was, because couldn't you then just say, well, the next one's going to be add 9, so it's going to be 1 over, 26. So that would allow you to generate the next number in the sequence. If this gap thing is fixed, as it is here, right, look for something to do with n squared. If this gap is the same number each time, in this case, it's plus 5. Look for multiples, right? So I'll give you one last example now. Would you agree you could probably figure out the next number, right? But we want to find a general formula. Right. Top number's 1. If I look at the gaps, add 2, add 2, add 2, add 2. That tells me it's a multiple. And the multiple will be whatever you add. So if you add 3 each time, it's going to be 3. If you add 5 each time, as we did up here, it's going to be 5n. That might not be the perfect answer, but it's half the answer. Can you look here that 2 times 1, 2 times 2, and 2 times 3 don't get you 3, 5, and 7? You see they're a little bit out, but aren't they the same amount out? So it would be 1 over 2n plus what? Plus 1? Yeah. Right. 2 times 1 is 2, but we want 3. 2 times 2, the second term, is 4. We want 5. 2 times 4 is 8, but we want 9. 2n plus 1. And see if the top number's 11 or something. That's the easy bit, right? What do you think you do if it goes plus minus on you?
Sure.
Right? So I see people going like that. Now, to the n or to the n plus 1? Because if you put n, you'll get a plus minus combination. And if you put n plus 1, you'll get a plus minus combination. But one of them starts with the correct one. Right? One of them starts with a positive and the other starts with a negative. So will it be n or n plus 1?
N plus 1.
Yeah. Think of that as 1, and that's 2, and that's n is 3, and that's n is 4. If you put in 1, right, the value of n, don't you get 11? But here you would get negative 11. So the plus 1 is the one that does it. And say hi, everybody, and bye-bye. Hi means
you.
for attendance.
Made like 4,000 cribbage boards that way. It was amazing.
What was that, Tim?
So
Sorry.
using like a very similar sequence to that, I had to write a program to make a whole bunch of cribbage boards because we were contracted to drill all of the little holes in a cribbage board.
Oh, interesting. And did you? How did you figure it out? Did you figure out the way we did it, or?
Well, you know that like you're gonna make I think they were 3/16 inch holes, so you need to know that you need to go over half a diameter to get to clear your hole, or actually a whole diameter to clear your hole, plus whatever spacing they want for the pins. The part, and that's for the straights. And then the complicated part is when you want to tell it how far to go triangularly, because a CNC doesn't. I mean, some of them can generate curves, but the ones we had were not fancy enough. So you'd have to give it an X and a Y to go each time, so that it could know its new position, so that it could generate that hole. And so I didn't write the most efficient program upon reflection, because I did one whole row of holes, and they snake around like an S. So I did one whole row, and then I come to this corner, and then it starts to do the second one. The more efficient way to do it would have been hole, 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 and then all the way around, so that we don't have this long tool path from one side to the other.
That's interesting that math and numerically controlled machines kind of came together for a little while.
If you want to do real fun trigonometry, I can show you some really fun trigonometry.
Done with numerically controlled machines.
Yeah, that's what taught me calculus.
Cool. I think if you can see it being used, or questions and problems that could be solved using it, it makes it easier to motivate yourself to learn it. Whereas if it's just numbers, and I'm not really going to do much with these, it's harder to motivate yourself. That was interesting.
Oh, it was really easy to motivate me to learn trig. It was, you learn trig or you lose your job. So I learned trig.
You asked because you work in the shipyard, right? Yeah, the shipyard is quite ruthless in their rules.
Yeah,
you will do it or you will lose your
Yeah.
job. Essentially, it's pretty severe. I don't think we should do that in the college, right? If you don't learn how to do sequences, we're kicking you out of college. You're not getting back in. I think that would be a bit cruel. I'm trying to think of another word. Hi guys, any questions? Are you just hanging about for whatever?
I have a question.
Oh yeah,
Go
I'll let
ahead.
you go first, Christian.
Go for it, Christian. What's your question?
I had a question on number 13.
13. Let's have a look at this guy. Okay, so we're trying to generate a formula for a really ugly looking sequence, because it's got everything that you could have in a sequence in it. The top is changing, the bottom is changing. And it's also got pluses and minuses. So I'm going to tackle this in stages. It's plus, then it's negative, then it's plus again, then it's negative. I know how to generate that. it's going to be generated by a -1 to the n, or it's going to be generated by a -1 to the n plus 1, right? That's how you generate plus and minus patterns, right? Now, the first term should be positive, right? The second term should be negative, the third term, and then the fourth term, right? So 1, 2, 3, 4. These are representing the n values. So all I do is I plug n equals 1 into this guy, and I plug n equals 1 into this guy, and whichever one matches, in this case positive, is the one I'm going to use. So -1 to the 1 is -1, and -1 to the 1 plus 1, which is -1 squared, is +1. Do you see I want this version? Because it is positive. So I've now got that out the way. So basically, forget about the pluses and minuses now. Right, they're done. Now we'll focus on the top. Do you see 1, 4, 9, 16, and 25? You see those guys on the top?
Yeah.
Do you recognize them?
Oh, they're the squared.
Yeah, the squares. There we go. 1 squared, 2 squared, 3 squared, 4 squared. Now, the bottom one, if we do that gap trick, do you see here you're adding 1 each time?
Yep.
If you did the gap trick, forget about the pluses and minuses. You're adding 5, you're adding, sorry, 3, then you're adding 5, then you're adding 7. If you ever see the gaps going up, like add 1, add 3, add 5, add 7, right? Add 2, add 4, add 6, add 8, right? You're looking at an n squared and stuff, right? In this case, it would just n squared, but maybe it's going to be n squared plus 4 or something, right? In another question. If, however, it goes up by a fixed amount, add 1, add 1, add 1, add 3, add 3, add 3, right, for example, then whatever you're adding is the multiple of n. So if this was add 2n, add 2, if this was add 2, add 2, add 2, add 2, I would start with 2n. Now, that in this case is 1, so it's just 1n. Then you have to fix it. N on its own would only get you 1. Then it would get you 2, then it would get you 3, then you would get you 4. Do you see the answer is out? Well, if 1 needs to become 7, don't you add 6 to it?
Right.
And 2 to become 8, don't you add 6 to it? And 3 to become 9, don't you add 6 to it? So once you've figured out what to add to it, you'll find out it works for all the others as well. And there is your formula.